Hello and welcome to the Advanced Thermal Management Materials webinar brought to you by Thermal News Magazine and Mr. Carl Zwieben. My name is Nick Deverschmidt. I am the editor of Thermal News Magazine as well as the program chairman for the Advancements in Thermal Management Conference. I'd like to thank everybody for their attendance. Today we have a great presentation here for Mr. Zwieben. Just to kind of go over some things. You're more than welcome to ask any questions. All the attendees are on mute mode at the moment. But if you see in your GoToWebinar toolbar, there's a question section, and if there's something that you want to ask throughout there, I'll collect the questions and then ask Mr. Zwieben at the end of the presentation. And there's also a chat if you're having any issues with your audio. If you have any audio problems, there is a telephone you can call in, or you can use your computer microphone or speakers. With that said, I'd like to welcome our presenter here today. As mentioned, is Dr. Carl Zwieben. He's an independent consultant on composites and advanced thermal materials, and was for many years the Advanced Technology Manager and Division Fellow at GE Aerospace, which was later acquired by Lockheed Martin, where he directed the Composite Materials Center of Excellence. And he's been an active member in the thermal management community, specifically for materials, for more than 25 years. So I'll hand it off to Mr. Zwieben now.
Pleasure to be with you all today. I'm going to talk about a rapidly developing technology in which I have been involved for many years. This is a large, complex subject, and we will only be able to touch on a few highlights in the time available. I was unable to present this talk at the meeting in Denver because of a family medical emergency. So this is what we'll be talking about today. I'll start with a general introduction to the topic. We'll then take a look at traditional thermal management materials as a point of reference. And from there, we'll look at a brief overview or short overview of advanced thermal management materials. We'll look at the very important issue of cost, followed by a discussion of applications in electronics and photonics. And then I'll get out my crystal ball and try to predict where this technology is going. And finally, we will finish with a summary and conclusion. The key issues, or thermal management is a key problem area in both electronics and photonics. And that consists of not only heat dissipation, but the related issue of thermal stresses, which can cause warping, fracture, fatigue failure, soft solder fatigue, and creep. Thermal stresses are caused primarily by use of materials having different coefficients of thermal expansion. This is an old Air Force slide going back to the 1980s, showing it's not a new problem. And what we have here is a ceramic package attached to a fiberglass printed circuit board. These have very different coefficients of thermal expansion, giving rise to very high stresses in the solder joints under thermal cycling. Thermal problems are well known even to the public. Here are a few examples. The Xbox 360 had a thermal problem, and $1 billion was set aside to cover that issue. NVIDIA reported a $150 to $200 million graphics processing unit thermal problem, and resulting in a stock drop of 24%. And if you look online, there are a lot of discussion of hot spots or heat issues related to iPad 3. Almost all of the key technology roadmaps cite thermal problems, and consequences are that heat dissipation often limits power levels both in microelectronics and photonics. This is a historical slide showing the increase in power in microprocessors. This is an Intel slide. More currently, the trend to lead-free solders increases the thermal stress problem because they have higher process temperatures. Another issue is that there are applications with high ambient temperatures, such as automotive under the hood, and obviously that complicates heat dissipation. Consumer product surface hotspots is another issue, the iPad 3 being one example. Weight or mass is important in many applications, certainly portable systems, systems subjected to vibration loads, and even if weight is not a direct issue, if an object is or product is subjected to shock loads during shipping, for example, or in service, that becomes an issue. Volume and thickness are decreasing. This is obvious, and of course cost is always a critical issue. One of the interesting things that we've found over the years is that thermal problems are similar for all semiconductors, both electronic and photonic, the power modules, microprocessors, RF. In the photonics area we have diode lasers, light-emitting diodes, displays, and so forth. And we find that advanced thermal materials are widely used in almost all of these applications. And they're the same materials in the different applications. If we look at the current state-of-the-art or state-of-the-art before the advanced materials were developed, we find that traditional thermal materials are inadequate for many applications. They go back to the mid-20th century, and they impose major design limitations. In response to those limitations, the materials industry has developed and is continuing to develop an increasing number of advanced materials with thermal conductivities up to 1700 watts per meter Kelvin. In comparison, copper's 400. Most of these materials have low coefficients of thermal expansion, CTEs. They have low densities compared to copper. I emphasize that they are at various stages of development from R&D to high volume production. And we find that some are actually cheaper than traditional materials. So here's an example of the success that has been achieved with one advanced material, AlSiC, which is aluminum reinforced with silicon carbide particles. Oipek and Infineon reports that replacement of copper with AlSiC in IGBT module bases, they get a match of CTE to the aluminum nitride substrate, or they can match the CTE of the aluminum nitride substrate. This eliminates solder joint failure and increases lifetime from 10 to 30 years. So here's an ultrasonic image, or ultrasonic images of, on the left, an IGBT module with a copper base plate, and we can see that there's significant failure of the solder after only 4,000 cycles. On the right, we have a module with an AlSiC base plate, and after 20,000 cycles, there's no indication of solder failure. So in the paper on the subject, the author reports that the failure mechanism, referring to solder joint failure, does not exist any longer. So clearly, CTE match is advantageous in this application. There are numerous traditional and new thermal materials. Many engineers I've found in my short courses are only familiar with copper and aluminum. And that is, they're not familiar with a lot of the materials that have low coefficients of thermal expansion. Time constraint limits coverage of both traditional and advanced materials, so I have selected a few to talk about. There's more complete coverage in 1 day to 3 day short courses that I teach for various scientific and technical organizations, commercial organizations, and also in-house. And I have some papers on the subject that I can send you if you're interested. This talk focuses on materials used in all kinds of heat sinks, heat spreaders, and closures, and we don't touch on the important topic of thermal interface materials. This is another Air Force slide that I've modified slightly. Again, it goes back to the 1980s, and it shows the different packaging levels. Level 1 being the individual package, level 2 the printed circuit board level, and in military applications there's typically a heat sink or a cold plate, also called a thermal plane, attached to the printed circuit board. The level 3 is the subsystem or chassis, and I've added level 4, which is a support structure. And we find that advanced thermal materials are being used in levels 1, 2, and 3. Level 4 is more structural. Advanced composites are being used there for structural applications, but typically heat dissipation is not an issue in the support structure. So as a point of reference, let's take a look at traditional thermal management materials. If we look at semiconductors and ceramic substrates, which is basically what we're trying to package, we find the CTEs range between 2 and 7 parts per million per degree Kelvin. So to minimize thermal stresses, what we need are heat dissipation materials, that is thermal management materials, that have CTEs, coefficients of thermal expansion, in the range of 2 to 7 parts per million per degree Kelvin. So that's our target. Here's a list of traditional thermal and packaging materials. Don't have time to go through all of them, but I'll point out that at the bottom, e-glass epoxy, such as FR4 printed circuit board, has extremely low thermal conductivity. It's actually really a thermal insulator. If we look at the CTE, I've gone through many papers and manufacturer's data, and you find reported coefficients of expansion ranging between 2 and 24 parts per million per degree Kelvin. 17 or 18 is a typical number. So that is an issue in itself, the high coefficient of thermal expansion of e-glass epoxy printed circuit boards. So let's take a look at limitations of traditional materials. Copper and aluminum both have high coefficients of expansion. Copper 17, aluminum 23, and recall we're shooting for 2 to 7 parts per million per degree Kelvin. The result is thermal stresses and warping. Consequently, we require use of underfills or compliant thermal interface materials, abbreviated TIMs, such as greases, polymeric solders, and so forth. If we look at copper, another problem is that it has a high density, 8.9 versus 2.7 for aluminum, so it's roughly 3 times the density of aluminum. And that's an issue in weight-critical applications. So let's take a look at these compliant thermal interface materials. Greases have very low thermal resistance, which is why they're widely used. However, they are messy to apply, and they are susceptible to dry out and pump out, and also silicone migration. There are other polymeric thermal interface materials. The major problem is high thermal resistance, and increasingly these polymeric TIMs, thermal interface materials, are often the greatest contributor to the total system thermal resistance. Another approach is to use compliant, or also called soft solders, which are mostly indium-based. And what is meant by a compliant or soft solder is that it has a very low yield stress. Because of the low yield stress, it has poor fatigue life under thermal cycling. And we all know that if we have a paper clip and we bend it back and forth above the yield stress, it fractures, and that's the example of the fatigue life of metals that are cycled above the yield stress. These soft solders are also susceptible to creep, formation of intermetallics, corrosion, electromigration, and they're relatively expensive. If we look at traditional low-CTE materials, they all have significant deficiencies. They are materials like tungsten, Covar. Covar is a nickel-iron alloy, molybdenum, alloy 42. Molybdenum copper is actually a metal-metal composite. It's not an alloy. Copper Invar copper is a laminated material. Titanium and there are other examples of low CTE materials. One of the big issues is that most have thermal conductivities that are less than or equal to that of aluminum alloys, roughly in the range of 200 watts per meter Kelvin. They all have high densities except for titanium. They're relatively expensive, especially things like copper tungsten, and very hard to machine. So the bottom line is that to minimize thermal resistance and solder fatigue, it's desirable to use direct attach with hard solders. However, that requires either a CTE match in the materials or the use of an underfill. So here are some examples of traditional materials. Copper tungsten, again, which is a composite material, really a family of composite materials, in which we can tailor the CTE by varying the weight ratio of copper and tungsten. Again, it's not an alloy because the copper is not soluble in the tungsten at room temperature. So you see that by varying the weight ratio of tungsten to copper, we can achieve CTEs, coefficients of expansion, in the desired range of roughly 2 to 7 parts per million. However, if we look at the densities, they're extremely high, roughly twice that of copper. Another traditional material, or really a laminated material that has been used, is copper Invar copper. The Invar actually is a constraining layer that allows us to tailor the coefficient of expansion of this laminate by selecting the ratio, a thickness ratio of copper to Invar. And again, you see we can achieve low coefficients of thermal expansion. Notice that this laminate has an anisotropic thermal conductivity, that is, it varies with direction. So we have a horizontal conductivity that's much higher than the vertical thermal conductivity. As we saw earlier, E-glass epoxy printed circuit boards and generally most other circuit board materials have high coefficients of thermal expansion, requiring either underfill or some kind of constraint. So if we just use an unconstrained printed circuit board, we have high thermal stresses requiring the use of underfills. Now, for many years, at least in the aerospace industry, copper Invar copper constraining layers were used to reduce the coefficient of expansion of this printed circuit board assembly. That is, copper Invar copper was bonded to the fiberglass and reduced the coefficient of expansion of this bonded assembly. And what we're finding, as we'll see later, is that new materials are replacing copper Invar copper, with advantages in weight and also thermal conductivity. So with that background, let's take a look at advanced thermal management materials. They are a steadily emerging group of materials, as I mentioned, from various stages of development, from R&D to large volume production, and they're well established in an increasing number of production applications, at least some of them are. Advantages are thermal conductivities up to 1700 watts per meter Kelvin compared to 400 for copper, and they're also thermal insulators if needed, but we focus on the thermal conductors. With advanced materials, you can tailor the coefficient of thermal expansion of the group of materials from -2 to +60 parts per million, so we can virtually match anything. Not with every material, but with the assembly of materials. Some are cheaper than traditional materials. Some have tailorable electrical resistivities. Some have very high stiffness and strength, which is important for structural applications or vibration critical applications. Almost all have densities that are lower than copper. Some can be made by net shape processes. Net shape process is one that requires no machining. And some allow incorporation of ceramic substrates and feed-throughs, which can eliminate some labor steps. disadvantages. Many are higher cost. It may require some development cost to implement a new material. That is, some of them are not necessarily drop-in, some are not. A few of the materials display hysteresis, as does copper Invar copper. Some are hard to machine, some are hard to metallize. Emphasize that most of these problems have been solved. Not for every material, but for many of them. Galvanic corrosion potential is an issue for carbon aluminum, and plating may eliminate this problem. Some display porosity, for example, like aluminum castings. Therefore, some are not hermetic, but they can be plated, many of them, to correct the hermeticity problem. Payoffs are improved thermal performance, certainly, enabling higher power levels, increased efficiency. The CTE match reduces thermal stresses, warping, and distortion, increases reliability. We get reductions in weight and size, reduced power consumption, possible elimination of underfills. With some materials, we can tailor the electrical conductivity and use that to reduce electromagnetic emissions. At GE, we found that by eliminating some fracture problems in manufacturing by matching CTEs, we were able to save $60 million on one project. And as I mentioned, there's a low cost potential for these new materials, and we'll talk about cost later on. We can divide advanced thermal materials into several classes. We have monolithic carbonaceous materials, that is, there are various forms of carbon. Then we have composite materials, and I define composite as two or more materials bonded together. That distinguishes composite, say, from metallic alloys where one metal is dissolved in another. Composites have been used for many years in electronics, so FR4 printed circuit boards consist of woven e-glass fibers in an epoxy matrix. Copper tungsten is a composite, as I mentioned, and so forth. We can further break down composites into several categories. We have polymer matrix composites, abbreviated PMCs. We have metal matrix composites, MMCs, carbon matrix composites, CAMCs, and ceramic matrix composites, CMCs. We also have what some people consider alloys, other people consider composites because the materials come out of solution at room temperature, and so I'm calling them metal-metal alloys-composites. And again, time constraint limits materials we can talk about. Let's take a look we'll start with a discussion of monolithic carbonaceous materials. Again, these are just various forms of carbon. One of the most important is flexible graphite, previously called natural graphite. It consists of exfoliated natural graphite and possibly other forms of graphite. Materials are highly anisotropic. They're flexible. They are a foil-like family of materials. They are anisotropic so that they have low through-thickness thermal conductivity. That can actually be a benefit by reducing surface hotspots in consumer products. Notice that this family of materials has low range of densities. Thermal conductivities as high as 1500 watts per meter Kelvin in plane. Through thickness conductivities are very low. It's almost a thermal insulator in plane, and, which is an issue, but you can get around that problem. These materials are being used in a lot of applications. Notice that the in-plane CTE is actually negative. That's not a misprint. Carbon in some directions, various forms of carbon in some directions have negative CTEs. As I mentioned, flexible graphite is flexible. If you need a rigid plate, such as for a heat sink. You can combine natural graphite particles with epoxy to form rigid plates, and you can get thermal conductivities in the in-plane in the range of copper. Through thickness is still lower. You get a negative in-plane coefficient of thermal expansion and a density that's significantly less than that of aluminum. Another carbonaceous material that's being used, at least in military applications, is highly oriented pyrolytic graphite, abbreviated HOPG. It's a weak, highly anisotropic material. Because it's weak, it's typically encapsulated with a metal or a composite. We see that it has in-plane thermal conductivities up to 1700 watts per meter Kelvin, much lower through thickness thermal conductivity. In-plane CTE, again, is negative, and the density is 2.26, which is lower than that of aluminum. Let's take a look at composite materials, and there are really many different types of composites. We only have time to touch on a few. These are the reinforcements that are used in composites. At the upper left, we have continuous fibers. These provide the highest structural efficiency, highest thermal efficiency. We have discontinuous fibers and whiskers. A whisker is simply elongated single crystal. And then we have CNTs, that stands for carbon nanotubes. We'll talk about that later on. We can take continuous fibers and weave them into fabrics and braids. So, for example, FR4, as I mentioned, is a woven glass fabric impregnated with epoxy. And we also have particle reinforcements and flakes, which is a flat type of particle. In this chart, we look at the coefficient of expansion of a family of materials made by introducing silicon carbide particles into aluminum alloys. This material is typically called AlSiC, Al for aluminum, SiC for silicon carbide. And here we look at the coefficient of expansion of AlSiC as a function of particle volume fractions. And we see that as we increase the particle volume fraction on the horizontal axis, we get a reduction in the CTE of AlSiC. Initial material was made by powder metallurgy. We now have a number of infiltration processes that allow higher particle volume fractions and CTEs, coefficients of thermal expansion, that match aluminum oxide and get very close to that of silicon. So let's take a look at AlSiC in a little more detail. This was the first advanced thermal management material. Work was started at GE in the group that I ran back in the 1980s. The original material was made by powder metallurgy. It's now made by multiple processes and manufacturers. It's well established in commercial and aerospace applications. Some processes can produce net-shaped parts that require no machining. Can be significantly cheaper than copper tungsten and copper moly, in addition to being lighter. One type, it's really a family of materials, one type is reportedly cheaper than copper. And as I mentioned earlier, Oipek and Finion reported that use of AlSiC in place of copper eliminated fatigue failure in IGBT modules. Here's a summary of the range of properties that you can get with AlSiC. There are multiple suppliers and processes. The properties depend strongly on the composition and the process. So we have particle volume fractions ranging from 20 to 70%. Densities are in the range of aluminum alloys or slightly higher. Notice we can get a range of CTEs, so we can match ceramics, we can match printed circuit board, fiberglass printed circuit boards. Range of thermal conductivities up to 255, which is actually higher than that of any aluminum alloy I'm familiar with. And notice that the modulus has, we can get moduli up to 250 gigapascals compared to 70 for aluminum. So if you look at stiffness to density, which is critical for vibration applications, this material has significant advantages. And we'll see later it has been used in printed circuit board cold plates where it benefits the vibration situation. Another metal matrix composite, MMC, consists of aluminum reinforced with graphite platelets. This is an anisotropic material. Densities are somewhat lower than aluminum alloys. Thermal conductivities have been achieved up to 750 watts per meter Kelvin. Again, it's anisotropic, so through thickness thermal conductivities are much lower. And notice that we can achieve low in-plane CTEs in the range of 4 to 7, and our goal is 2 to 7, depending on what type of semiconductor or ceramic we're trying to match. We have a family of diamond particle reinforced metals. These are all metal matrix composites. Matrix materials are copper, aluminum, silver, cobalt. Properties are isotropic, that is, they're independent of direction, so this through thickness and in-plane conductivities are the same. Thermal conductivities have been achieved, in this case, with a silver matrix up to 983 watts per meter Kelvin, so we're approaching 1,000 watts per meter Kelvin in an isotropic material. Again, CTEs are tailorable and low, and densities are lower than that of copper, depending on the matrix and particle volume fractions. So far, the only composites we've talked about have been metal matrix composite. We also have a ceramic matrix composite, CMC, that originally was called, by the original manufacturer, originally called diamond silicon carbide. Diamond particle reinforced silicon carbide. It's now manufactured by a different company, Element 6, and they refer to it as silicon cemented diamond, the abbreviation SCD. Both companies used SCD as their abbreviation. Density is about 1/3 that of copper. It's got a low CTE and thermal conductivity up to thermal conductivity of about 600 watts per meter Kelvin. This material was used in an IBM server for a while. Talked about copper invar copper, which has been used as a constraining layer for printed circuit boards. This is a new material. This is a polymer matrix composite consisting of carbon fibers in a polymer matrix. There are a number of different matrix materials, a number of different polymers available. Properties are highly anisotropic. We see that the material has a low density and, importantly, very low in-plane coefficient of thermal expansion, so it is useful to constrain the CTE of the printed circuit board. Material also has fairly high stiffness, so it can be beneficial in vibration critical applications as well. So another class of composites, another class of materials I talked about are variously considered to be alloys or composites. This one consists of silicon and aluminum, and at room temperature the silicon comes out of solution, so you have regions of silicon that are bonded to aluminum. This is really a family of materials with various particle volume fractions of silicon from 40 to 70%. Notice the densities are lower than that of aluminum. It is a family of materials, and we can tailor the CTE from 7 to 13. Thermal conductivities are lower than many aluminum alloys, but still useful for many applications. And as in the case of AlSiC that we talked about earlier, this family of materials has higher moduli than aluminum, so it's advantageous for stiffness critical applications such as vibration dominated applications. Let's take a look at cost, always a critical topic. This is a complex issue. Many factors affect cost. Obviously, the cost of the reinforcement and the matrix materials, process cost, state of development, laboratory versus factory. For example, the first ALSIC parts that we made at GE cost hundreds to thousands of dollars a piece. You can now buy microprocessor lids in high volume production for $2 to $5 a piece. Tooling cost, if we're using injection processes, for example. Part size, which is the volume of material, the complexity of the part, tolerances, flatness, roughness, size of the production run. So it's a complex issue. In general, many advanced materials are more expensive than traditional, but some are actually cheaper. There is a potential for lower cost, both at the component level and the system level. So, for example, at the system level, higher power may enable fewer devices, may enable convection cooling instead of liquid cooling, reduced cooling power consumption if we can use natural convection, for example, reduces the lower total cost of ownership. And an expensive material can be cost effective depending on what the alternatives are. So, for example, the Apple PowerMac G5 liquid cooling parts cost about $100 in addition to installation labor. And liquid cooling, if there are leaks, as there were with some of the PowerMac G5s, result in expensive repairs. History has shown that cost tends to decrease as production volume and technology maturity increase. In addition, the material volume in many parts is quite small. Net shape processes and near net shape processes can reduce machining cost. Consolidating process steps such as incorporation of feed-throughs and substrates also reduce labor cost. However, if you do that, the effect on rework becomes an issue. So the bottom line is the only way to get a real handle on cost is to get a firm quote. We talked about a number of materials. Let's now take a look at some applications. Diamond particle reinforced cobalt metal matrix composite drill bits have been used for many years in rock drills. Here we have traditional material, molybdenum copper, which is a metal matrix composite, and this is just a picture showing a variety of traditional parts. These are the first ALSIC parts, or at least modules. We made some carriers earlier, but around 1985 we were trying to replace Covar, a nickel iron alloy, and so we looked at ALSIC, metal matrix composite on the right, and we got a weight reduction of about 2/3, and we achieved roughly 10 times the thermal conductivity of Covar. This chart shows a so-called hybrid approach to packaging. The lead frame is Covar. You can see the leads projecting through this Covar lead frame. The base plate is ALSIC, and here we have silicon carbide particles, and the silicon carbide particles are combined with aluminum alloy to form this composite base plate. These are ALSIC microprocessor lids, and as I said, in high volume production, these are available for as low as $2 to $5 a piece. This is an aerospace application. A power module base here is ALSIC replacing copper tungsten, and the weight savings is 85%. That's higher than I've ever seen achieved with structural composite. And this is pretty much a drop-in application. So it's just an illustration of the very dramatic potential for weight reduction with advanced materials. In addition to weight reduction, we get possible benefit in size reduction. Here we have a base station carrier. At the top is the copper baseline. At the bottom is an ALSIC replacement. Because of the difference in coefficient of thermal expansion, the copper substrate required multiple small aluminum oxide or alumina substrates, but by matching the coefficient of thermal expansion with ALSIC, these multiple small plates could be replaced with one large aluminum oxide substrate. Mentioned diamond particle reinforced metals. I showed you some drill bits in a previous slide, which I'm showing you here again. But I'll point out that diamond particle reinforced metal matrix composites have been used in industrial applications for decades. So in addition to the rock drills, we have on the left a grinding wheel blank composed of diamond particle reinforced copper. So those that composite, diamond particle reinforced composite, has been used in grinding applications for a long time. So the argument here is, or my thought here is, that if the material is cheap enough to be used in drilling rocks or grinding applications, it certainly merits consideration, at least in high-end thermal management applications. Talked about diamond particle reinforced silicon carbide, sold under the trade name SCD, now silicon cemented diamond. So here's an example of a heat spreader. Heat spreaders made of this material were used in IBM servers for a while. This is a diamond particle reinforced silver metal matrix composite base plate, or I should say this package has a diamond particle reinforced silver base plate. It's a metal matrix composite, and this is for a high power gallium nitride spacecraft application, and you get a significant improvement in thermal conductivity. And you can see in this chart on the lower left, or this figure on the lower left, that here's the thermal conductivity on the vertical axis versus temperature. The lower red diamond particles are copper tungsten, and the square particles in black are silver diamond composites. Working our way up the packaging level, we have ALSIC printed circuit board heat plates. The advantage here, high stiffness for vibration and low coefficient of thermal expansion. Using liquid cooling helps with heat dissipation, but it does not eliminate the issue of thermal stresses arising from materials with different coefficients of thermal expansion. So we find that ALSIC, aluminum reinforced with silicon carbide particles, is used in liquid-cooled heat sinks as well as rigid heat sinks, solid heat sinks. Talked about flexible graphite. It's used in smartphones, tablet computers, and displays. As I mentioned earlier, a highly oriented pyrolytic graphite is a brittle material, and it's typically encapsulated with aluminum. So here we have an example of that. This is a layer of highly oriented pyrolytic graphite, and these are the aluminum encapsulating layers. Talked about use of stable core carbon fiber reinforced polymer composite that's used to reduce the coefficient of thermal expansion of printed circuit board materials. So here we have a single printed circuit board computer used in a spacecraft application, and it's a fiberglass printed circuit board bonded to stable core layers, which reduce the coefficient of thermal expansion of the assembly. Working our way up again now to level 3, we have an electronic enclosure that incorporates metal matrix composites. The composite has 2.4 times the thermal conductivity of aluminum, and it's 10% lighter, and this is a production part. If we now turn to photonics, this is some work we did at GE many years ago, and this is a concentrator photovoltaic array. So the incident sunlight bounces off this mirror and is concentrated on a gallium arsenide photovoltaic cell, which is attached to a beryllium oxide support. Now, the beryllium oxide was chosen because it has a high thermal conductivity. As we all know, the photovoltaic cells are only only convert part of the incident energy to electricity. The remainder has to be dissipated as heat. So in the original design, the beryllium oxide block was attached to aluminum spiders, and because of the high coefficient of expansion of the aluminum spiders compared to that of beryllium oxide, the solder joints failed under illumination. So what we did was to redesign these spiders using carbon fiber reinforced aluminum. We matched the coefficient of thermal expansion of the beryllium oxide block, and that eliminated the solder joint failure. These spiders are also electrically conductive, so they conduct the electricity, and they have a higher stiffness than the aluminum, so from a mechanical standpoint as well as a thermal and electrical standpoint, it met all the requirements. And that was actually lighter than the aluminum spiders. This is an example of a hybrid approach to thermal management. And here we have a thermoelectric cooler substrate or pedestal, or have a thermoelectric cooler substrate, and in the pedestal region where the thermoelectric cooler is mounted, here this hybrid approach utilizes a highly oriented pyrolytic graphite, trade name TPG, inserted into an ALSIC component, into ALSIC components. The ALSIC matches the CTE of the ceramic substrate, and the highly oriented pyrolytic graphite provides greater heat spreading in the pedestal area. Again, this is a hybrid approach. You don't have to be limited to one material. Again, going back to flexible graphite, we find a number of applications in solid-state lighting where they make use of flexible graphite to dissipate heat. As in the case of the photovoltaic cells, LEDs, light-emitting diodes, are only partially efficient, and so there's a lot of heat that has to be dissipated. They don't radiate heat as incandescent bulbs do, so there has to be materials with high thermal conductivity to get rid of the heat. If we now look at where the technology is going, we find that thermal management undoubtedly would continue to be a problem in electronic and photonic packaging. And as I mentioned, all of the roadmaps predict this and indicate that thermal management problems are not likely to go away. 3D architecture adds complexity to the thermal management problem. We're likely to see continuing development of new materials, both monolithic carbonaceous composites, thermal interface materials, which we didn't have time to talk about today. Reinforcements, carbon nanotubes and nanofibers are of considerable interest. Smalley estimated the thermal conductivity of carbon nanotubes potential is 6,000 watts per meter Kelvin, which is really quite remarkable. We have graphite platelets, diamond particles, which have thermal conductivities up to 2,000 watts per meter Kelvin. And we also have electrically non-conductive particles, and diamond would be a good example of that. But there are others. I think we're likely to see thermally conductive, electrically insulating materials with high thermal conductivities. Right now, we don't have a lot of, we have very limited potential in thermal conductivity for electrically insulating materials. Very interesting experiment that was reported recently indicates the thermal conductivity of certain type of spider silk as high as 400 watts per meter Kelvin. I emphasize this was preliminary results of just one paper. If verified, that could open the door to inherently thermally conductive polymers, which is a very exciting possible development. We have the hybrid approach to thermal management, again, using two or more materials. We showed some examples. And there are numerous other possible materials. So to summarize, thermal management is a critical problem in both electronic and photonic systems. And the problems are heat dissipation and thermal stresses resulting in warping and fracture. Weight and size are important in many applications, and as we've seen, traditional thermal materials have significant deficiencies. In response to those deficiencies, material suppliers have developed and are continuing to develop an increasing number of advanced materials. At this point, we have thermal conductivities up to 1700 watts per meter Kelvin, low tailorable coefficients of expansion, low densities. Some are actually cheaper than traditional materials, and applications are increasing steadily. Finally, if we look at these materials, the advanced materials, they go back 3-4 decades, roughly, actually 3 decades at most. In the history of technology, 3 decades is barely the blink of an eye. So in my view, I believe we are in the early stages of a thermal materials revolution. So I thank you for your attention, and I'll now be happy to answer any questions.
If anybody has any questions, feel free to type it in, or if you want to raise your hand on the attendee list area, and I can unmute you and I can ask Dr. Zwiebman directly. Either one will work. But I did have a question at first here concerning some of the materials that were discussed. For example, the flexible graphite have low through thickness thermal conductivities. How would you deal with this?
Excuse me. The first thing to do is use an anisotropic finite element model or other analytical model that incorporates anisotropy to determine whether the through thickness and in-plane properties of the materials as it exists are adequate, and you may find that they are. If they're not, there are tricks you can use, like incorporation of thermal vias.
Okay. Great. Could you maybe explain the future of carbon nanotubes in thermal materials?
Single-wall carbon nanotubes have predicted thermal conductivities as high as 6,000, as I mentioned in the talk. But to date, measured conductivities have been measured as high as 3,000 watts per meter Kelvin, which is higher than diamond, except there are some forms of diamond that have 3,300. As I mentioned, the theoretical prediction is small as 6,000. However, carbon nanotubes are quite small, resulting in many thermal interfaces, which cause phonon scattering, so that it may be difficult to realize the thermal conductivity of these carbon nanotubes in a composite. So in general, I think we need more research in this area.
Okay, maybe you could discuss the thermal conductivity of injection molded materials reinforced with discontinuous carbon fibers?
We didn't have time to cover all of the materials, as I mentioned, all of the advanced materials. There are a number of injection molding compounds that use discontinuous reinforcements, carbon fibers and other materials. I point out there are many types of carbon fibers. Some have low thermal conductivities. Others have conductivities as high as 2,000 watts per meter Kelvin. So injection molding compounds using discontinuous fibers have much lower conductivities. So for example, with continuous fibers you can get in-plane conductivities as high as 300 watts per meter Kelvin, which is 50% greater than that of aluminum. But with injection molding compounds, they're typically much less than 100. However, there are many applications that are convection limited, and in those cases the thermal conductivities of these injection molding compounds have been shown to be adequate. So it's worthwhile doing the analysis because the injection molding process can produce some very inexpensive parts.
All right. Actually, I have one last question here. Are there ways to use some of the more expensive materials in cost-sensitive applications?
There may well be applications for which expensive materials are cost-effective as is. So, for example, that gallium nitride package that I showed you earlier would be one example.
Mm-hmm.
However, there are many cases where it is not, in many cases, it is not necessary to make the entire component out of one material. So basically, you want to minimize the use of expensive materials. So in this case, you can combine the expensive material, which has high thermal conductivity, with other materials such as AlSiC, for example, that are cheaper, and you place the expensive thermally conductive material in regions where heat dissipation is most critical. And as I mentioned, this is referred to as a hybrid approach. So the thermoelectric cooler pedestal I showed earlier, which combined highly oriented pyrolytic graphite and AlSiC, is a good example. And also I showed you a package with a Kovar lead frame and an AlSiC baseplate. That's another example of the hybrid approach.
All right, great. Does anybody have any questions? And if not, we'd definitely like to thank everybody for their attendance today. And if you have any questions, certainly Dr. Zubin's email is there, and he can answer anything directly. But otherwise, we'd like to thank everybody for spending an hour of their day today, and we'll let you know if we have any more in the future. Thank you.